All right, I want to take this few minutes just to set up something that is often not taught in introductory physics courses, but it would be useful for you to consider carefully um, as we begin to approach the doing of problems. Um, and this applies really for both electronic homework and homework that you turn in by hand. Um, One of the dangers or temptations, I guess I should say, with online homework systems is not to fully set up and do problems. The problem with that, and I understand why people don't often fully write up their solutions to problems. The problem with that is you're not thinking through the problem solving techniques that we will learn. Um, if all you're doing is plugging numbers into a calculator and sketching out some chicken scratch that you won't be able to read later, your homework that you do online isn't going to be much service to you. You'll do it, you'll get points for it, and then you'll forget it. Um, Possibly this might be fueled by online homework systems that people use in high school. I see it in my own daughters and try to address it with them. And I'm going to do the same thing here. So I really think it's important for you to fully write up your solutions to homework problems that you're doing, regardless of whether you're turning that work in or not. Just a bit of advice, and let me tell you, it makes a big difference, both in your retention of um, techniques to solve problems, but also in remembering doing the problems themselves, actually, so that when you see problems that are similar on an exam, for instance, you'll be better equipped to handle them. So I'm going to suggest a method. It's not magic, but really, I do believe that helping students learn to solve problems efficiently and fully is one of my most important things as a professor. Systematic approaches to problems really are important. I want to help you be organized in your thinking too, so that you're able to apply physical principles to a wide variety of situations which may or may not be familiar. The systematic approach that I suggest here is found if you look in Night in Tactics Box 1.5. So there's a reference there, and I'm following a similar method, similar ideas. The systematic approach that we'll talk about helps you to figure out what the situation dictates and what not, and sometimes, very importantly, what information you really need, and what information you can discard, you don't need. I would argue really that one half of problem solving, and that's a low estimate really. It may be 3/4 of problem solving is setting it up. Setting up the problem. Doing so in a way that makes problem solutions easier to come by. Really, really is critical. So one of the things that I would suggest that you do is include, perhaps if it's a kinematics problem like we're doing, um, perhaps a motion diagrams, a motion diagram. It may be helpful just to get you thinking, okay? May be useful. Um, but a really important thing to do is to set up a coordinate system, okay? You may have a car, let's say, that's moving horizontally. So it is useful to just draw something like this and label it with X, or label it if you want vertically with Y, or you can even be unconventional and label vertical motion by X if you like, or S, as Knight does frequently in one-dimensional problems. It really is an essential part um, of setup. And you are really free to orient axes any way, any direction you want. There is absolutely no need for you to make the x-axis the one that's horizontal at all. You can, if you have motion, let's draw a motion diagram for something that maybe is going up a hill like this. There's absolutely nothing that says you can't make that the x-axis and that the y-axis. It may be more convenient. Why would it be more convenient? It may be more convenient in this case than maybe a more traditional X and Y like that. Why? Because in the tilted setup, the motion is confined to one dimension. All right. And as we will see, one-dimensional problems are easier to do, more compact in their notation. And so why not make your coordinate system as simple and as convenient as it can be? That's a big, big piece of advice for you. It may be helpful. Another thing that would be helpful would be to draw a sketch. So suppose what we have here is a person on a bike going up a hill. So I've drawn my coordinate system, X and Y. Here's my terrible attempt at drawing a bike. And we start at this location, X equals 0. And let's say we finish at X final equals 20 meters. And maybe we want to even sketch the bike up at that time. Okay. Really is helpful for you. Especially, I say, this is very much like advice you're going to get in lab, by the way. Especially if you want to come back 2 months later, you're studying for the final exam, you're looking at problems that you did. If you don't fully sketch them, if you don't be very systematic in setting them up, it's going to be very hard for you, not impossible, but very hard to reconstruct what you did in the problem. Same thing again will be said in laboratory when talking about looking at your lab book 2 months after you've done the lab work, if you need to refer to it. Okay, so a sketch, motion diagram, coordinate system, all these are really helpful. Coordinate system is absolutely essential. Motion diagram and sketch are helpful um, for putting things together. Often my technique is usually sketch first, then perhaps coordinates, then motion diagram. If a motion diagram is going to turn out to be helpful. Okay. Along with this is define any other symbols. If you've got a coordinate system put together, then you've already got your coordinates that you'll use. But there may be other symbols that are helpful, like initial and final velocities. Maybe acceleration, if acceleration is a constant. Something like that. Next thing you'll want to do for sure is to list the information that you know and that you don't know. Okay, so maybe you get a table. Maybe you make a table of all of the things that you know here For instance, in the problem that I started to do up above, I know x initial, I've defined it to be 0. You can define the 0 to be anywhere, by the way. I define my x final to be 20 meters. Let's suppose I have v initial equals 0.0, v final equals something I don't know, and let's say a equals 3.5 meters per second squared. All right, that would be a nice set of information for us to have at the outset. I probably need to know one more thing, like delta t equals, 2.0 seconds or something, maybe. All right, and make sure that you highlight by underlining or some other method, highlight the unknown information, and then you can proceed to set up your algebra. Okay. So that's what we would, I guess, call a comprehensive setup of a problem that then you would go on further and solve. Okay. So just as another example, let's just fill out one more set. Okay. Suppose we have a car. This is just a problem that I'd pull out of the air. Starts at some initial v0, ends at some at v2 equals 0, and let's say it's a problem where I have v0 equals 20.0 meters per second, and some intermediate time I've got some velocity v1 equals 20.0 meters per second, and then at that time the car hits its brakes. Let's suppose we're also told that x0 equals 0 and x2 equals 60.0 meters. And let's suppose we know that v2 is equal to 0, v1 is 0, v1 is 20 meters per second, v0 is 20 meters per second. Let's suppose we also know t0, our initial time, we're going to call 0.0 seconds. And our intermediate time, the time when the brakes are applied, is 0.50 seconds. Let's suppose that's the information that you are given, and you need to figure out what is the acceleration. Okay? So, we have the problem statement is we have a car that is beginning at some point in time and coasts at a velocity of 20.0 meters per second for half a second before applying the brakes because it saw a deer jump into the road or something. And let's say that from the beginning, from time 0 to time t2, the total distance of travel is 60 meters. And we want to know then, therefore, what is the acceleration of the car as it is braking. Okay, so to set this problem up, here's where I would go. I'd say, here's my car, and here is my coordinate system. X increases in that sense. And we said there's this intermediate time. We don't know where the car is exactly, do we? No, in fact, we don't know where it is. But we know that at this location, we label this as x1. We can label this stopping point. So let's draw the car again as it is stopped. That is x2. Here is x1. We know at this point in time, just draw a little velocity vector v1. We can draw a little velocity vector, it should have been an x0. That should be a v0. That should be a v1. And we know that V2 is equal to 0. Okay? We could draw a motion diagram just to clarify our thinking here. So we've got constant velocity motion, right? Until the car reaches x1. And then it rapidly begins to slow down as it's braking, right? I didn't mean to make those spots smaller. They don't have to be, obviously. And we know from the previous discussion, I'll just reproduce them here, that x0 is equal to 0.0. That x2 is equal to 60.0 meters. I should always label with units. We don't know what x1 is right away anyway. We know that v0 is 20.0 meters per second. We know that v1 is 20.0 meters per second. And we know that v2 is equal to 0.0 meters per second. And we know also that our initial time, we can call it 0.0 seconds. Our time T1 intermediate time is 0.50 seconds. And we do not know T2. And finally, we are asked for the variable a, assuming a constant acceleration from time T1 to T2. Okay? Now, how to proceed after this is a question of constant acceleration problems that we'll be dealing with in class. But this is the setup. Okay? Good setup gives you a good foundation for complete, honestly efficient problem solving. Okay? If I had a quote book, that would go in it. All right? Careful setup of a problem where you've defined your variables very carefully is really important in successfully navigating the world of problem solving in physics. So that's all I've got for us today on this, and I hope this has been helpful. We'll see you in class.